A car is traveling on a road in hilly terrain, as shown in the figure below. Assume the tops and bottoms of the hills have a radius of curvature r. The driver of the car is most likely to feel weightless at which position? So here are the two positions that we have. So let's start with the first case here, where the driver is at the bottom of the hill. So I'm going to quickly draw a free body diagram. Pointing up, we have normal force, and pulling it back down, we have the force of gravity. And since the hill is kind of like a circle, or a semicircle, the driver is going to be undergoing circular motion. So since this is at the bottom of the circle, there is going to be a centripetal acceleration towards the center of the circle. And the positive x direction will be pointing radially towards the center of circle. So this is going to be pointing towards the center of the circle. So with that, we can use Newton's second law, which says that the net force, or the summation of all of the forces acting on an object, is equal to that object's mass times its acceleration. So in this case, the only two forces are the normal force and the force of gravity, and the force of gravity is pulling it down away from the center of the circle. And that must be equal to the mass times the acceleration, where the acceleration is the centripetal acceleration towards the center of the circle. And if you remember, the centripetal acceleration is given by v squared over r. So we can substitute that in. Normal force minus the force of gravity is equal to the mass times v squared over r. So the normal force is equal to the force of gravity, mg, plus mv squared over r. And I put the force of weight in front to show you that the normal force is actually greater than the gravity, because it also has to provide the centripetal acceleration towards the center of the circle. So in this case, the normal force at the bottom of a hill is actually going to be greater than the force of gravity, or the weight of the car. So the driver is going to feel a lot of weight at the bottom, or a lot more force. And now let's draw a free body diagram for the top of a hill. So we're going to have a semicircle like this, and here's our car. Down we have mg, or towards the center of the circle we have mg rather, and up we have the normal force. And this time the acceleration is going to be downwards, the centripetal acceleration, since the center of the circle is going to be below the car if he's at the top of the circle. And this time our positive x direction is still towards the center of the circle, but since the car's at the top of the hill, the center of the circle is actually going to be in the opposite direction as it was when he was at the bottom of the hill. So in this case, the force of gravity, or mg, is actually going to be positive. So mg minus the normal force, and this is the normal force when the car is at the top, must be equal to ma(c), where ac is the centripetal acceleration. And we know from earlier that the centripetal acceleration is simply v squared over r, so we just plug that in. Now all we need to do is solve for the normal force, square of r minus mg. So normal force is equal to mg minus mv squared over r. So in this case, the normal force is actually smaller than the force of gravity, since the centripetal force required is subtracted from the force of gravity. So these are our calculations here. I'll erase this part. So the driver will most likely feel weightless at the top of the hill. That's our answer. And if you think about this, it would make sense, since at the bottom, the normal force needs to apply both the centripetal force, this is the centripetal force, as well as oppose the force of gravity. that's actually pulling it down. So the normal force needs to provide both the centripetal force and the force of gravity. Well, at the top of the hill, the centripetal force is partly provided by the force of gravity. So the force of gravity goes to help kind of produce that centripetal force towards the center of the circle. And that is how you would solve this problem here.